Okay, it's my pleasure to introduce our speaker today, Dr. Irene Shivaei. Irene got her PhD here at UC Riverside. That was Brian.
Yes.
Yeah, she got her PhD in 2017, where she was an NSF graduate fellow. After that, she was a NASA Hubble fellow, and she was like a part of the MIRI team during the commissioning years of JWST. And she was, after that, she was, till 2023, she was a research faculty at the University of Arizona in Tucson. And since 2023, she has been a research fellow at the Astrophysics Department of Centro de Astrobiología in Spain. Yeah, so please welcome me, join me in welcoming Dr. Irene Shivaei.
Thank you. Thanks, Nilüfer. Hi, everyone. Thank you for having me. I'm very upset that I'm not there in person. So hopefully another time, I'm sure in the future, it will happen that I will see you all again in person. But thanks for having me today, even though online. It's a pleasure to talk to you about some of our recent work on this topic that you see the title of, studying dust properties in galaxies, basically beyond the local universe, with a main focus on results that come across with JWST and ALMA. But first, I'm going to start with a little bit of an introduction. To me, dust is like the cosmic rich 1% of the population. And that's because by mass, it's actually a very small, negligible fraction of the total content of the universe. From the baryonic mass or the total mass content of the universe, dust mass is very negligible and small. But even though by mass it's a tiny fraction, it has major roles in terms of energetics. If you look at in this plot, and this is the spectral energy distribution of the universe, of course, cosmic microwave background dominates the SED of the universe. But if you look at the emission that comes from extragalactic radiation, extragalactic backgrounds, so from galaxy evolution and formation, half of it is cosmic infrared background, which is the dust reprocessed light. We know that in terms of physics and chemistry of the ISM, dust also has very important key roles. It's basically the solid phase of metals in the ISM of galaxies. It has important roles in the star formation, planet formation. It's catalyst for formation of certain molecules like H2. Has roles in the cooling and heating of the ISM, and the list can go on and on. It also shapes our view of galaxies by attenuating the UV and optical light and re-emitting it at longer infrared wavelengths. So whether you look at images of galaxies or you study the spectra of galaxies, however you want to, whatever parameter that you're curious about to derive from your observations, by not accounting, without accounting the effect of dust, you will have systematically large biases in your interpretation. So, for example, up to a factor of 10 in star formation rates or a factor of 5 in stellar masses, you can underestimate your values. So the effect of dust, we can see it across the spectrum. In the UV and optical wavelength by attenuation, there are multiple measures of dust attenuation by dust. I listed some of the very common ones. For example, looking at the slope of the UV continuum emission, looking at the dust attenuation curve of galaxies, or looking at the nebular emission and how that is attenuated, for example, looking at Balmer line ratios. But we see the effect of dust also in emission at longer infrared wavelengths. Very simplistically talking, we can divide it into two components. The warm dust component emits in the mid-infrared, and from the star-forming region, we have the PAH emission. These PAHs are polycyclic aromatic hydrocarbons. These are layers of carbon molecules with edges of hydrogen that they absorb UV photons and get transiently heated to high temperatures and re-emit at certain wavelengths in mid-infrared. The strongest of one is this broadband at about 7.7 micron. But we also have warm dust coming from around the AGN. AGN is a highly emitting source that can heat up the dust to very high temperatures. And that component shows up as a continuum power law in the mid-infrared, which I'm not showing here. But that's the mid-infrared warm dust part of the emission. We also have the far infrared emission, which is coming from larger grains. These are dust grains that are in thermal equilibrium. So they are thermally heated, and their emission in a simple way can be modeled as a black body emission with a peak that shows the dominant typical temperature of dust in the ISM. So as you can see, the effect of dust is across the spectrum. And by knowing its importance and the key roles that it plays in the galaxy formation and evolution processes, there are still main unresolved questions that we would like to answer in this field. I've listed them in very simple ways into these three categories. Generally, how much dust there is in the universe, from low redshift all the way to the high redshift. What kind of dust it is, what are the properties of these dust grains, their chemistry, their size distribution, their origin and their evolution, where are they coming from? And where is this dust located in galaxies? So these are all very big topics. For this talk, I'm going to mainly focus on the first two questions, and particularly at redshifts greater than 1. And why is that? So in the past few decades, there has been a lot of studies that looked at properties of dust in the local universe. There's a wealth of data, multi-wavelength, spectroscopic and photometry. There are still, of course, unknowns, and not everything is solved, but I would say that its dust properties of local galaxies are very well explored, which is also very nice because it gives us a very solid base to compare to studies at higher redshifts. But the situation is not as nice as we go to higher redshifts. At cosmic noon, Herschel and Spitzer were both really revolutionary. They opened the infrared universe to us. And there are many studies that parameterize the properties of dusty galaxies at cosmic noon that comes from data from these two space telescopes. Also, ALMA. ALMA has a high sensitivity, but has limited field of view. So it's very much complementary to what Spitzer and Herschel were able to do, which were survey telescopes. And all three together have revealed a lot of information about dusty galaxies at high redshift. But the problem is that most of these studies are biased to bright infrared populations. And this is just inevitable because of the sensitivity limitations of Herschel and Spitzer. So if you go to higher redshifts in the early universe, we know that dust exists in very high redshift galaxies. In the past decade, the history of ALMA combined with discovery of high redshift galaxies that was pre-JWST with Hubble, large amounts of dust has been identified and discovered or observed in very high redshift galaxies, all the way into the reionization era. But the samples were very small, and that was just because of the limitations, again, the sensitivity limitations of these telescopes. So all I'm saying is that when we move to redshifts beyond the local universe, we are basically looking at the tip of the iceberg, the small samples that are biased to the most obscure population of galaxies. But this, of course, have now changed with James Webb in multiple ways, because of the wavelength coverage and the sensitivity of this amazing telescope. So the main part of my talk is going to be in two parts. First, I'm going to talk about the attenuation properties of high redshift galaxies, so redshift of 3 or 4 and above, which is coming mainly from advancements that we are having with JWST. This is coming from JWST near-infrared instruments that are probing the rest frame UV and optical emission of high redshift galaxies, so giving us observations to constrain the attenuation parameter. And then the second part of my talk, I will move to slightly lower redshift cosmic known galaxies, looking at now dust emission. So particularly PAH emission from mid-infrared instruments on James Webb, and ALMA looking at cold dust and cold gas component of cosmic known galaxies. Okay, so now first part. As you all know, the attenuation curve of a galaxy shows the amount of dust attenuation as a function of wavelength, which we can parameterize it in a very simple way. For a foreground screen of dust in front of your stars, the attenuation curve of galaxy defines your observed spectrum of the galaxy, which means that if you know the shape of the attenuation curve, you can correct your observations to derive the intrinsic fluxes and intrinsic properties of your galaxies. But the problem is that we don't know the shape of the attenuation curve of galaxies, and it's a property that changes from galaxy to galaxy. Even in the local universe, if you look at extinction curves of Milky Way, SMC, or LMC, there are large variations in particularly the slope of the attenuation curve, which is commonly parameterized as the slope of the curve at 1500 angstrom to V band, so 5500 angstrom. And also this feature, UV attenuation bond, which is a very broad attenuation feature centered at around 2100 angstrom. And it's very dominant in Milky Way. It's nearly absent in different sight lines of SMC. And as we go to higher redshift, there are a lot of different studies that some see it in some type of galaxies, and it's not always, but it's not always there. So all these uncertainties means that our UV measurements and optical measurements of galaxies are inevitably subject to large uncertainties if we don't know the shape of the attenuation curve. So what determines the shape of the attenuation curve? One parameter is the geometry of dust with respect to stars. So how is dust located with respect to the emitting sources, the stars? There are multiple studies, theoretical, that show that, for example, in here, if you have a shell of dust around your stars, or if you have a homogeneous distribution of dust or a clumpy distribution of dust compared to your stars, the shape of your attenuation curve, both the slope and the strength of the UV bomb, can change. But the shape of the attenuation curve also depends on dust grain properties, their composition and size distribution. Larger dust grains, if you have a larger fraction of small dust grains, your attenuation curve slope will be steeper. Depending on whether your dominant dust population is from silicate grains or carbonaceous grains, again, those can change the shape of the slope of the attenuation curve. And of course, these two parameters are very much related to each other, which means that if we parameterize the attenuation curve of a galaxy, it's very difficult to disentangle these two properties. But at the same time, it means that there's a lot of valuable information about the origin of dust and the properties of dust in the attenuation curve of individual galaxies. So that has motivated many studies, both before and now with JWST, about what is the main driver of the change in the attenuation curve of galaxies. So in the left, I'm showing some of the papers that has been done over the years for redshift 0 to cosmic known galaxies. A few years ago, we had this study that we saw there is a large variation with the metallicity of galaxies, such that low metallicity galaxies have very steep slopes, like an SMC curve, and high metallicity galaxies are much shallower and have a very strong bump, like the Milky Way extinction curve. Now, recently with JWST, there are multiple studies that sort of actually give a mixed message. For example, here in this study, they used a few hundred galaxies with near spectra, and their main conclusion is that there's probably a redshift evolution in the slope of the attenuation curve, such that at higher redshifts, we are getting a much shallower slope. But it's hard to put all of this into a big picture because these studies are subject to sample selection biases. The samples that we have near spectra for are very inhomogeneous and very difficult to understand how they change from redshift 2 to redshift 11. So that brought me to the idea of this work. In order to avoid the sample selection biases as much as is possible, I put together large samples of GRISM spectra. These are coming from 3 large GRISM campaigns, Frisco, ALT, and Congress surveys. The advantage of this data set is that with GRISM data, you are basically selecting flux galaxies, flux limit. You will have a flux limited sample of galaxies across different redshifts. So the idea is that with the GRISM, you can detect multiple lines, and with those multiple lines, you will robustly determine the redshift of the galaxy. So here I'm showing a few examples of redshift 7 galaxies on the left, and on the right, redshift 2, 5, and 4. So these data sets are very rich, and they survey the sky in multiple filters, but give you, depending on the redshift of the galaxy, give you a large sample of galaxies across redshifts. So all of these put together, there are about 4,000 spectroscopically confirmed galaxies from redshift 1 to 9. So you can see the distribution, the redshift distribution of these. Different colors show samples from those different 3 GRISM campaigns. But in total, from redshift 1 to about 9, there are about 4,000 spectroscopically confirmed galaxies in this work. So once we have these, important property of them is that we know their redshift. We went and fit their photometric data using Prospector, particularly here, which is the flexible SED fitting code with parameterization for the dust attenuation curve, which I will get to it in a second. What I want to highlight here is that all of these galaxies have a wealth of NIRCam and HST data. And as you can see, because of the way they are selected, these are emission-lined galaxies effectively, you can see very strong emission lines across redshifts, from redshift 2 all the way to high redshift. All of them have very strong emission lines. So this is a little bit of math about how we fit for the attenuation curve. We assume the typical 2-component dust model, which means that you have a dust component that is around in the birth cloud of your stars, and you have another component that is in the diffuse ISM. When your birth cloud component is going to affect only your youngest and most massive stars, and your diffuse dust component will affect the light from all populations of stars. And then in this fitting, the slope of the attenuation curve is set as a free parameter. So we're fitting for that along with other parameters in the SED fitting. So once we do this for the galaxies, we will have observed SED, which is coming from the fit to the photometry. And then we can also, we know the basically intrinsic or zero dust SED of the galaxies. And by comparing these two, we can derive the attenuation curve. So here is the main result. The most prominent factor that defines the change in the attenuation, the slope of the attenuation curve in this sample is the optical depth at V band. So for galaxies with high optical depth, high amount of dust, we see a very shallow curve, which is shown in red here. And as the low optical depth galaxies, the sample has a steeper curve. So in the background, I'm showing the black curves show some of the attenuation curve that I showed earlier at redshift 0, or the low and high metallicity curve at high redshift. So in another way to show the slope of the attenuation curve parameterization for the whole sample, here on the left, I'm showing the slope, which is parameterized as the value of the curve at 1500 angstrom, so in the UV to V band, as a function of optical depth. And you immediately see that there is a very steep anti-correlation between these two. Low optical depth galaxies have much higher slope, also with a larger scatter. And as we go to a higher optical depth, we get to much shallower slope. So we see this observation, and this is also not the first time that this correlation has been observed. But it's interesting to a little bit dig deeper to understand why we are seeing this strong relationship. So we started comparing with different simulations. These are a set of simulations that use dust radiative transfer models from scared code implemented into hydro simulations of Milky Way type galaxies. So it's a single galaxy, but it's the novelty of these models is that the dust evolution is happening in the simulation. So it's not a post-processing, which was the common thing to do in the past. So there are a lot going on in this plot. The black contours are the data sets that I showed in the previous plot. And the red and green points are the simulations. The difference between them is in one of them, the size of the dust grains is evolving, and in the other one, the grain sizes are static or fixed. Each contour has one galaxy, so as the galaxy ages, the size of the circles grow. And from here to the top, the different shading of the symbols shows the inclination of the galaxy. So as you can see, the interesting thing is that almost all of this trend can be explained simply just by changing the inclination angle of the galaxies. More edge-on galaxies have shallower curves even though with the age of the galaxy evolving. And as we go to face-on inclinations, we get the shallower slopes. In other words, if I look at the slope of the attenuation curve, this time as a function of UV optical depth, so A at FUV wavelengths, we see that most of our galaxies are in the optically thin regime in the UV, which means that most of these galaxies can be, the slope of their curves can be explained by having a high fraction of their young stars unobscured by dust. So this was very interesting because this is a very simplistic model in terms of the properties of galaxies are actually not changing. It's a Milky Way-like galaxy, and we know that that is not the case for the full population of our galaxies from redshift 1 to 9. So we went one step further. We compared it with literature observations, and we found this very interesting trend. So again, the black contours are our galaxies from redshift 1 to 8. At redshift 0, there is this study by Salim et al. 2018 that they have thousands of galaxies from SDSS sample, and they fit the slope of the attenuation curve in a similar way. And what we see is that at a given optical depth, all of our galaxies have shallower slope compared to the redshift 0 galaxies. So even though within our sample, we don't see any redshift evolution, which I didn't show a plot for, but there is no redshift evolution from 1 to 8 within our sample. But when we compare it with this redshift 0 sample, it seems to be a shift. So to understand this trend, we compared the data with another set of simulations. These are hydro simulations of these galaxies. Again, dust is simulated, the dust evolution is simulated within these galaxies. But the difference here is that these galaxies they have a range of masses, metallicities, and gas fractions. So their starting points are very different from each other. So each cloud here is from one set of simulations. These two clouds, the red and green, are for galaxies with very large halos. So these are very massive, giant galaxies. The red ones are basically simulated to mimic local universe late type galaxies. And you can see that they very nicely match the trend in redshift 0 observations. And the green ones, these are still very massive, large halos, but also very star-forming with high gas fractions, so more starbursty galaxies. And you can see that this does explain the tail of our observations going to higher optical depths. Now, if I add the third set of simulations, these are smaller halos, lower mass galaxies. They're very young. They have very low starting metallicities and very high gas fractions. And you can see that they do show the same lower slopes at a given optical depth that we see for our observations compared to redshift 0. So what we think is happening is that there are two main channels for dust production. There is ISM growth, so metal accretion in the gas phase of the ISM forms dust grains, but preferentially small dust grains. And then there is a stellar origin, which mainly is supernova ejecta, and those produce larger dust grains. So the slope of the curve is very sensitive to the size distribution of dust grains. As you go to larger fraction of large grains, your slope gets shallower. So what we think is happening is that for these galaxies in our sample, these are, remember that they were emission line selected. So they are highly star-forming, high gas fractions. And they mimic these simulations that have very low starting metallicities. So there's not enough metals in the gas to start the ISM growth process. So the dust in these galaxies are probably dominantly from the stellar origin from supernovae ejecta. And their sizes are larger, so that's why we see these shallower slopes. Well, this is a very interesting finding because we can actually say something about the origin of these of dust in these galaxies. Now, we also look at, in a different study, look at a different sample of galaxies, this time in terms of their nebular dust properties. So on the y-axis here, I'm showing dust color axis, dust attenuation coming from Balmer decrement ratio of H alpha to H beta as a function of stellar mass. And also in this study, we compared it with redshift 0 galaxies. We don't see any real evolutionary trend. It seems like from redshift 0 to redshift 3 to 7, which is this study, everything more or less follows the same track. Of course, we are going to much lower stellar masses and much lower dust content. But if you compare the Balmer decrement, so the y-axis here, with the UV continuum slope of these galaxies, the trends are very different at these redshifts compared to redshift 0 to 2, but there are multiple factors that is going into this plot because UV slope is sensitive to other parameters other than dust as well. And indeed, we do see that if there is a clear correlation with the specific star formation rate of these galaxies, so high, the vertical trend, the UV slope changes with the specific star formation rate as well. Okay, so this is the end of the first part, which was the dust attenuation properties of high redshift galaxies. So I thought I will just pause for a second for the mini summary. I showed a study that we are looking at how what is the determining factor in changing the shape of the attenuation curve of high redshift galaxies. And we see that there is no redshift evolution if you select the sample in the same way from redshift 1 to 9. But compared to a different type of galaxies that exist at redshift 0, we see that our galaxies have dust that is dominantly coming from supernovae ejecta. And then in the other work, we're looking at dust attenuation in the nebular region, and we see a very large scatter of UV slope at a given Balmer decrement, which is correlated with age and specific star formation. All right, so for the second part of my talk, as I mentioned, I'm going to talk about lower redshift galaxies. So now at cosmic noon, redshift 1, 2, 3, and looking at their dust emission properties. But first, to show you why this topic is now hot and important to study, here I'm showing typical SED of infrared SED of typical galaxies at here now specifically 1.8, but cosmic noon in gray shading. And the arrows show the depth of data that we had with Spitzer, particularly MIPS 24 micron in the mid-infrared, and Herschel packs at 100 and 150 micron. So these are 3 sigma depths for Herschel, and this is the confusion limit for Spitzer MIPS. And as you can see, they were only able to pick out the most bright galaxies at these redshifts. And we were missing a large population of typical main sequence galaxies that had lower infrared luminosities, lower dust contents. But now with MIRI, this has completely changed. With very modest integration times of 10 to 30 minutes, we can go an order of magnitude or more deeper and pick out the dust emission of a large fraction of typical galaxies at cosmic noon. And this plot basically is showing the effect of higher sensitivity of MIRI instrument on JWST, but that's not only it. JWST MIRI also has a much higher spatial resolution compared to the previous telescopes that we had in this regime. And to show that, this is a footprint of a survey of the MIRI US GTO survey, SMILES, in 3 colors. But I want to zoom in on one example. This is on the bottom, you see the NIRCam image of 5 galaxies at around cosmic noon, so 0.8 to 2, redshift 0.8 to 2.3. And of course, the NIRCam resolution is amazing, and you can see all these galaxies individually. But this is what we had on the top right from in the mid-infrared with the Spitzer MIPS 24 micron. It's just one single giant blob, very difficult to even separate the emission of these galaxies. And now with MIRI, you can see this slide is going to show the image of MIRI of this part of the sky in 15 micron, 18 micron, and 21 micron. The data is just beautiful and is unprecedented and is enabling us to have SEDs like this for the first time at these redshifts. Amazing coverage from res frame UV all the way to far infrared, combining HST, JWST, and ALMA all the way together. So this galaxy, we're lucky that also has Herschel detection. That's not always the case for cosmic noon main sequence galaxies. But I don't know if there's anyone in the room who works in the local universe. If that's the case, you might be used to seeing these kinds of SEDs, but at high redshift, as the rest of you all know, having this sort of wavelength coverage is really just mind-blowing. So with this wealth of data, there's a lot that we can study about the properties of particularly PAHs, so emission from these molecules in the mid-infrared. And now we can very well constrain it, and we can study their properties. So I'm going to just go through very quickly some of the highlights of some of our recent results. So one of the important properties of these molecules is what is the mass fraction of dust that exists in PAHs. And at redshift 0, this has been studied a lot, and this trend with metallicity is very well established, that at low metallicities, the PAHs are preferentially either not produced or they are destroyed because of the different ISM conditions in low metallicity galaxies. But at high redshifts, they have a higher fraction. This hasn't been studied in depth for individual galaxies at high redshift, but now we can do it for cosmic noon galaxies with MIRI. You see the same mass fraction of PAHs on the y-axis as a function of stellar mass and converted to metallicity on the top axis. And we see very similar trend as for redshift 0 galaxies, high PAH fractions at high masses, high metallicities, and low PAH fractions at lower mass, lower metallicities. And just to remind you, this is the parameter space that was accessible to us with the Spitzer for for studies of individual galaxies. And now with JWST, we are going to much lower stellar masses. We can also look at what fraction of light or star formation in galaxies is obscured by dust. This is a study based on Spitzer MIPS data that looked at the fraction of obscured star formation compared to the total star formation rate of galaxies as a function of stellar mass. But as you can see, all of these data, all of this information is based on stacking. It was impossible to have individual measurements of individual galaxies. But this has completely changed now. With MIRI, we can individually measure the amount of obscured fraction in these galaxies. And you can see that we can go down to very low stellar masses, below 10 to 9, which is amazing. So this is the moving median trend that we see in the data. Just to compare it to what has been seen with Spitzer, the dotted line is the same line as in the left panel, so before JWST. And as expected, there is a difference because those studies were biased to more obscured galaxies, so you get a higher obscured fraction with the Spitzer data than what actually exists out there when you have a more sensitive telescope. The interesting thing is this plot is that if I draw a 50%, a line at the 50% obscuration fraction, so half of the light of these galaxies is obscured by dust, you can see a non-negligible number of very low mass galaxies that have more than half of their light obscured by dust, which are very interesting and need more in-depth study of how come, given their very low stellar masses, they had time to produce so much dust and have such high dust obscured fractions. The other thing in this plot that you might have all noticed is that there's a huge scatter at any given stellar mass. There's a very large scatter in the obscured fraction. And then we looked at properties of galaxies in the diagonal, in the vertical direction in this plot. We see that it mostly correlates with the size of the galaxies and particularly the star formation surface density. And this is, again, another parameter that now we can measure because with the MIRI data, we can measure actual star-forming sizes in these galaxies. And we see that more compact galaxies with higher star formation surface densities are the ones that have higher obscured fractions. We can also correlate the PAH properties to the cold gas. This is a synergy between JWST and ALMA that now has become possible. But first, a little bit of what has been done before JWST. So this plot shows the PAH luminosity as a function of CO luminosity, which is commonly used as a proxy for molecular gas mass. And both in terms of integrated values at redshift 0 and also resolved measurements of redshift 0 galaxies, in the literature, there are studies that saw very tight correlation. And the correlation extended to high redshift as well. But before JWST, again, it was limited to very bright, infrared bright galaxies, ULERGs, SMGs, etc. And that's this population up there. With MIRI, we looked at this relation for more typical main sequence galaxies. So these are CO observations from ALMA combined with MIRI observations for the PAH constraints. And we see that the main sequence galaxies also lie on this very tight relation. This relation is very promising because observing PAHs, constraining PAHs for cosmic noon galaxies is much more affordable than observing CO going down in the mass and metallicity regime. And this tight correlation is telling us that we can use PAHs as a proxy for molecular gas mass of galaxies in a much more realistic way for large samples down to lower masses and lower metallicities. We can also look at how the pHs correlate with the UV attenuation bump. So the UV bump that I mentioned earlier in the talk is commonly thought its origin to be the pH. So these molecules absorb the UV photons and produce this bump and emit in the mid-infrared. So with the Spitzer, we looked at whether we see a correlation between the emission and attenuation for a sample of cosmic noon galaxies, but again, based on stacks. Now, there's a student at CAP in Madrid that she's looking at this relation, but for a larger sample of individually measured pH emission combined with UV bump measurements from rest frame UV spectra and combined with metallicities coming from either cake or JWST NIRSpec. So stay tuned for that result. It's an ongoing study. But if you really want to understand pH physics, we need spectroscopy. So all of the results that I've shown you so far has been based on photometry, which will give you the general strength of the brightest pH emission. But to understand the physics of pHs and how those grains particularly are in terms of their charge and their size distribution, we need to look at the ratio of different pH bands, and that requires a spectroscopy. And even with JWST, that is very expensive. So we had a program in cycle 3 called POSPEX, which was aimed to get MIRI MRS spectra of 5 ALMA selected galaxies. So these galaxies are shown here. They're more or less on the main sequence. One of them is an AGN. And even though it's only 5 galaxies, this program was about 50 hours. We got the data a few months ago and spent a lot of time in figuring out the MRS data reduction, but the preliminary results are really exciting. This is the spectra of 2 redshift 1 galaxies, main sequence typical, and this is the first for on-lens galaxies. You can see multiple pH features in the spectra, also multiple lines, argon and neon lines. And the idea is to look at the ratios of these different features, which compared with models can tell us about their ionizing fraction and also their sizes. So again, stay tuned for more results on this. It's also ongoing. So before I finish, this is a small summary of what I talked about, properties of PAHs at cosmic noon with metallicity, with CO luminosity, and how it can tell what it tells us about obscured luminosity fraction of galaxies, and also about the attenuation properties. But the last topic that I just want to quickly flash is baryon cycling galaxies. If we really want to understand how cosmic noon galaxies are evolving, or generally how galaxies are evolving, it's not only dust. We need to put together multiple properties of galaxies, of the ISM of galaxies, to understand the interplay of gas, dust, and stars. So this plot shows edge of a molecular cloud that is irradiated by massive stars. So it's just a schematic way to show you that we need to know the metal content, metallicity, the dust content that can come from PAHs or the general dust emission, and also the molecular gas, which commonly for galaxies, we observe it with the CO emission. So this idea, since a few years ago, we started to study, to put together these 3 components for cosmic noon galaxies: gas, metals, and dust. We looked at dust to gas mass ratio as a function of metallicity, which is a very important diagnostic plot to understand the origin and evolution of dust in galaxies. Also looking at properties of dust and how it changes with metallicity. So finding that we have much hotter dust in general at low metallicities compared to solar metallicity galaxies. But as you can see, the number of galaxies in the low metallicity regime has been very limited. only a few individual detections. And that is shown in another way here. These data points are from the FIPS survey. This is the largest existing campaign, well, so until a few months ago, largest campaign at redshift greater than 1 that had all these different measurements, metallicity, dust, and molecular gas together. And you can see that it's very sparse, very few galaxies here and there. So in this cycle of ALMA, we got a large program approved called ALMA Chemical Evolution Survey that aims to get CO and dust continuum observation for a sample of 25 galaxies that very nicely fills up the mass metallicity diagram. So exploring the baryon cycle in this parameter space that has been unexplored so far. So here I'm just going to show you some of our, we got the data, a couple, like the last data came in 2-3 months ago. So this is just showing some of this data. On the left, you see the dust continuum contours on top of NIRCam images of these galaxies. And on the right, some of our CO detections that range from very low metallicities, some of our lowest metallicity galaxy, to higher metallicity galaxies. And we of course also have some non-detections. So these are all studies that have been ongoing to look at the properties of dust as a function of metallicity and also molecular gas budget and evolution of it as a function of metallicity and redshift. So again, stay tuned for more results, hopefully soon. And my last slide, I just wanted to have also a glimpse to the future, what we are looking forward in terms of major facilities that will tell us a lot about cold ISM. PRIMA is a concept for a 1.8 meter diameter telescope, cryogenically cooled to low temperatures, 4.5 Kelvin. So it's an observatory concept for that is being developed for a competition that next year we will know the result of between for NASA to be approved. So it's a competition between this telescope, an infrared telescope, and an X-ray telescope. The instruments that are being developed or designed for this observatory are a spectrometer and an imager from about 25 micron to 230 micron. And there has been a lot of activity going on. You might be already involved in it, but if you're not, the exciting thing about PRIMA is that 75% of it is going to be geoscience. So there are very active community working groups. Me, along with Jed McKinney in Texas, we are leading the Galaxy Evolution Working Group. If you're interested, get in touch with me and join us in this working group. As I mentioned, this is a concept study at the moment, but as a community, we are pushing it to show the interest for having a far infrared probe that hopefully next year will be approved. And with that, I'll leave you with my summary slide. Thank you.
Once again. Thank you, Irene. I think we have time for some questions for Irene. Any questions here? Yeah, shoot.
When you in the first half, when you were calculating the dust from the SED fitting, did you make any assumptions about the attenuation curve during the fitting?
So the attenuation curve in that part is one of the parameters that is being fit. So the slope of the attenuation curve is a free parameter in the code.
Okay.
Is that you don't seem convinced?
Follow-up question on that. Like, what about the strength of the UV bump? It was not a free parameter, right?
That was also a free parameter. Yeah, and actually, if I go back to those. Sorry, I don't know why I stopped the show. So if I go back to this slide. So the slope, both the slope and the UV bump are free parameters. So these are these two parameters. But the thing is, the UV bump is very hard to constrain it with just photometry. And for the majority of these galaxies, it's not constrained at all. So it's just outputting not really the prior, because the prior is zero strength, but it's basically just not constrained. So in these curves, there is a small bump, but I won't trust it. On average, we can't constrain it. The only situations that you can constrain it is that if a galaxy is exactly at the right redshift to have multiple bands, shortward, longward, and on the bump.
Yeah, hi Irene, this is really interesting. Okay, all right. It's too interesting, I have too many questions, so I'm just, my one question is annoying. When can I read this paper? Is it almost done?
Well, almost done, yes. I learned that transitioning from a postdoc to actually leading a group means I don't have enough time for science.
I'm aware of this phenomenon.
Yes, exactly. That's why I'm saying it, because I remember all of you saying it at that time, and I didn't believe it. But yeah, so I mean, the work, as you can see, all the plots are there, so it's very close to finishing. But yeah, it's soon.
Okay, yeah, I'm just gonna say we're very interested. I know this would be super useful for us, so looking forward to it.
Thanks.
I think I have a question from Gabby.
Yeah, absolutely amazing work, Irene. It's a great talk. I'm kind of really excited about the correlation between a PAH and the CO. But the problem is that for me, to use it myself, is that the 3.3 micron PAH is so much more accessible, both, depending on which setup you have on JWST, and also if you are doing higher redshift. I know that this may be a very obsolete question. I know that FANGS has done a whole bunch about line ratios, but do you guys have plans to extend this to the 3.3? Is there a way that it can be extended to the 3.3 micron?
Yes, very good question. So I'm gonna stop on this, but it's actually like I need another plot, which I don't have. Oh, actually, I might have it. So with this data set, for large samples, it's very difficult because with photometry, you can't really constrain the 3.3 micron.
Right.
All MIRI bands are too broad to get it. But I think the way to do it, which is one of the things we are going to do, is to use the spectra. The problem with it is that right now the sample is very small, it's 5. There is only one other program that has MRS spectra, and that is, I don't know if they have ALMA data. So, but for these 5 galaxies, we have CO measurements and we have the spectra. The 3.3 micron, very preliminary results, it might change, but it's acting very weird right now because it's much weaker than the model predictions. But yeah, I think the way to look at it is having larger samples of MIRI spectroscopy that shows 3.3 micron with ALMA data.
Okay. I'll wait. Thank you.
Sure.
Question?
Can I ask a question?
Yeah, go ahead.
Yeah. So regarding the change of UV bump and the slope of the attenuation curve with redshift, I wanted to ask how much of that change can we attribute to like the intrinsic change of dust properties in time, and how much of that is driven by the degenerate properties like a stellar age and like geometry and other properties?
I mean, everything about the dust attenuation and its variation is a more or less a degenerate problem between the property of the grains and the geometry. But I guess what I was showing in the trend that we were seeing with dust with the UV slope of the curve, so not the bump, but the slope of the curve, you can explain the whole trend that we see with geometry. But if you compare it with a completely different population of galaxies that we have at redshift 0, so more evolved systems, not as a star forming, not as high gas fraction, then you see that there is a difference, which cannot be only geometry, because we are comparing a sample of a few hundred galaxies with a few thousand galaxies. So it's an average, statistically average sample. So the geometry effect is random, so it can't be just the geometry. Then at that point, we are attributing the difference that we see to the properties of the grains.
If there's no other question, let's thank Irene. Thanks for joining us.
Thank you. Thanks for coming. Hope to see you all soon in person.
Yeah. Hope to see you here.
Have a nice day.
You too. Bye.